have studied about discrete time Fourier transforms. Let us see what is the significance of using discrete Fourier transforms. So there must be some limitations in your discrete time Fourier transforms which made us go into discrete Fourier transforms. Let us just summarize, okay, and look at what are the different properties of discrete time Fourier transform, what exactly make us shift from discrete time Fourier transform to discrete Fourier transforms. Okay, let us see this. The first point is, if the sequences are of finite duration, it forms a special case, and we shall see that it is possible to develop an alternative Fourier representation which you refer to as discrete Fourier transforms. Okay, if the sequences are of finite duration, okay, that means the sequences are finite, so they don't exist from minus infinity plus infinity, but they exist from certain finite ranges. Then it's a special case, and I can actually start implementing or using a separate Fourier transforms called as discrete Fourier transforms. Okay, let us understand this by first studying or summarizing what we already know about DTFT. Then we'll come back to DFT and see what is the significance of this type of Fourier transforms. Okay, let us look at discrete time Fourier transforms. So we are talking about a discrete time signal x of n. Then we know it is Fourier transform is represented by x of e to the power of j omega. You see here the DTFT is continuous function of frequency omega. This type of representation is computationally convenient, not convenient, and is representation of discrete time signal x of n. If we look at a discrete time Fourier transform as we have seen, let us take a discrete time signal x of n. As we have studied earlier, the discrete time Fourier transform is given by x e to the power of j omega. Now when you look at this DTFT here, it is a continuous with respect to frequency omega. So when I want to computationally calculate certain value for this, because this is continuous with respect to omega, it becomes a little difficult for us to compute the discrete time Fourier transform. So we have to look at alternatives. How can I develop a method which is computationally easy for us and which gives particularly for a finite sequence of signals? So let us look into that. If a sequence is represented by samples of its continuous spectrum, this type of frequency domain representation of a signal is known as discrete Fourier transform. That means if I have a continuous signal, then the continuous signal can be represented in terms of its samples, then I'll get a certain Fourier transform called as discrete Fourier transform. That means we are representing a sequence of input signals as a sample version of it, and I'll get a samples of it. That is my discrete Fourier transforms. Discrete Fourier transform is a sequence rather than a function of a continuous variable, and it corresponds to equally spaced frequency samples of DTFT of a signal. So let us read this again. The discrete Fourier transform is a sequence rather than a function of a continuous variable, and it corresponds to equally spaced frequency samples of a DTFT of a signal. So if you look at a DFT, that is discrete Fourier transform, unlike DTFT, which is a continuous with a certain function omega, here DFT will represent samples. So the samples are equally spaced, and it's of a DTFT signal. They are equally spaced of a DTFT signal, so I'll get a DFT for that. So DFT is used in transforming discrete time sequence x of n of finite length into discrete frequency sequence x of k. So what is it we are doing? Take a discrete time signal x of n of finite length, then I'll get finite samples x of k, that is the frequency representation. This is possible when I take into consideration DFT, that is discrete Fourier transform. DFT is used in transforming discrete time sequence x of n of finite length into discrete frequency sequence x of k, that is DFT. So what I'll get is, I'll take a x of n which is finite, then when I apply DFT to it, we'll get a sequence of discrete finite sequence x of k. Before actually we go into detail of a DFT, let us look at some of the facts which we already know. Some of the properties we have to just look at them in detail now, so that we will be able to understand DFT or a fast Fourier transform better. Okay, let's start with some important aspects. The first one is discrete convolution. The convolution is a mathematical operation or a tool which is equivalent to finite impulse response filter. Okay, it's a mathematical tool which is equivalent to finite impulse response filter, FIR filter. Convolution is very important digital signal processing. Convolving two sequences in the time domain is equivalent to multiplying the sequences in frequency domain. This we are all aware of. So that means when I take x1 of n and I convolve with x2 of n, so this will be equal to product in frequency domain. So that means x of e to the power of j omega or x2 into e to the power of j omega. So this is in frequency domain. We are just talking about what we have studied yet. So in time domain this is convolution, in frequency domain this is multiplication. This is one important point. Let's look at the other important points of convolution. Convolution application is used in processing signals, analyzing the output of a system. Okay, so convolution application is processing signals and analyzing the output of a system. So let us take this. So let us say x of n is nothing but x1 of n convolved with x2 of n. Okay, because this is a discrete case, will be summation. So this will be equal to summation k is equal to minus infinity to plus infinity x1 of k, okay, x2 of n minus k. So this is summation x1 of k, x2 n minus k. Or I can even write like this. This also I can write as k is equal to minus infinity plus infinity x1 of n minus k, x2 of k. Okay, so I can write this in both the forms. So this is the convolution in terms of discrete cases. In discrete cases, this is what you have to do. Next, an arbitrary signal can be represented in terms of the weighted sum of impulses. Any arbitrary signal I can represent in terms of weighted sum of impulses. Then let us see the other point. Response of a discrete time LTI system to arbitrary inputs is called as a convolution sum. So take an x of n input signal and y of n as the output. You will be passing through a discrete time LTI system h of n, and if the impulse is given as input delta of n, then the output response is called as h of n, that is impulse response. Okay, let us see this. Okay, I have a system. This is an LTI system. I am giving here x of n, this is my h of n, and this is my output. Let us say it is y of n. Okay, this is my input, is also called as excitation. Now I can give this as delta of n. Okay, so h of n will now determine what is the output when the input is a impulse. So y of n is called as an impulse response. So this is how we have to look at the, also understand this type of systems. Now let us see this. If x of n is equal to delta of n, then y of n is equal to h of n, h of delta n. Okay, if x of n is equal to summation k is equal to minus infinity plus infinity x of k delta of n minus k. So that is equal to h of n minus k x of k. As you see this sequence of steps, I will just go read this sequence of steps, that will you will be understanding this properly. If x of n is delta of n, that is I have given the input as a delta function, then what is y of n? Y of n is nothing but h of n, and that is equal to h, that is capital H of delta n. So x of n will be nothing but k is equal to minus infinity plus infinity summation x of k delta of n minus k, because it is convolution here. What is convolved? The input is convolved here. So the output will be the convolution of x of k and h of k, which is shifted. So h of n minus k. So what is h of n for us is delta, isn't it? So delta of n minus k. So that's what we have put, x of k delta of n minus k. So y of n is nothing but h of x of n. So h of summation k is equal to minus infinity plus infinity x of k delta of n minus k. Then y of n is equal to k is equal to minus infinity plus infinity x of k h of delta of n minus k. So h of delta of n minus k is nothing but h of n minus k. So that is y of n. This is one important convolution property which you should all be aware of. So what are the different steps involved in the convolution? The first step is folding. Fold the signal h of k about the origin k is equal to 0. That is the first step. You have to fold the signal. Then second is shift the signal. So what is that we are doing? Shift h of minus k to the right by n naught if n naught is positive, or shift h of minus k to the left by n naught if n negative, to obtain h of n minus n0 minus k. N minus k isn't it? We are seeing h of n minus k. So you have to do this shifting. That is the second property. Third is multiplication. Multiply y of k by h of n minus k, n naught minus k, to obtain the product sequence. Y of k is equal to x of k into h of n0 minus k. So you have to multiply this. Then finally summation. Sum of all the values of the product sequence y0 of k to obtain the value of the output at time n is equal to n0. So these are the steps. First you have to fold, then you have to shift, then you have to multiply, then you have to add. So this is how you get the convolution sum. So let us say two signals are being convolved. X of n is convolved with h of n. So there are two ways I can write this. The first way is I can write this summation of k is equal to minus infinity plus infinity, x of k and h of n minus k. This is one way. Or I can have a second way of representing this, that is I can write this as k is equal to minus infinity to plus infinity, h of k first, then x of n minus k second. So these are two ways I can do convolution sum. Okay. So again all the four steps which we have seen we have to follow to get the convolution. This is how we can actually begin by discussing about the two different forms of convolution. So I can do these two different types of convolution. The first case is, if you see, or we have just seen, the first case is h of n is folded and shifted where x of n is input or excitation. The second case, x of n is folded and shifted where h of n is the input or the excitation. These are the different properties now of convolution are: it is commutative, it is associative, and also satisfies distribution property. So these are the three different properties of convolution: commutative, associative, and distribution property. So these three properties of convolution we should be conversant with, or we should know these three properties. Let us see an example on convolution. Okay, now the question is, we have to determine the convolution of two finite duration sequences given. One of them is x of n. This is convolved with h of n. We should find out what is the result of convolution. If you look at this sequences given, it says that x of n exists only for values of minus 1 and plus n. Okay, and it's having a value 1 and it is 0 elsewhere. Similarly, when you look at h of n is having a value 1 where n is less than or equal to minus 1 and plus 1. That means it is existing only in the duration of minus 1 to plus of n, plus of 1, and it is 0 elsewhere. When you look at these type of sequences, when I find the convolution, one best thing which we have to start off with is to understand this better. Let us have a graphical representation of these two, then understand where do these sequences exist, and when I do the convolution, then I will get the picture of what actually we are doing. So let us first draw this graphically. So when I look at x of n picture graph, it looks like this. Okay, this is my x of n. Okay, it is 1. So let us put this is plus 1 here, and this is minus 1 here, and also it exists at 1. Also this is existing at these places. So this is my x of n. As you see here, it is only limited to minus 1 plus 1, and it's 0 here. This is 2, this is 3. Okay, it goes on. This is 2, this is 3, minus 2, minus 3. So this is my x of n. When I look at the h of n also, how does h of n look like? H of n is like this, and if you see both of them are same, that means this is 1 here when it is 0, okay, and this is plus 1 and this is minus 1, and when you look at minus plus 2 here, this is 0, plus 3 it is 0. Similarly here minus 2 is 0 and minus 3 is 0. Okay, let us just separate these two. Okay, now we have seen the mathematical equation and also seen the graphical representation. So you see here, whatever is given mathematically, we have put it graphically here. So you see x of n exists minus 1, 0 and plus 1. H of n exists only at minus 1, 0, plus 1. So this is how the graphical representation looks. Now the challenge, or what we have to do is, the solution is, we have to find out what is the convolution of this. So earlier we have seen the formula. We will put down this formula here, and then we will try to understand how to calculate the convolution of such a sequence. Now let us put the formula which we know. So convolution of those two signals, let us say we represent the convolution of two signals of y of n. So this is equal to summation k is equal to minus infinity to plus infinity. Okay, what are the two signals given? X of k and h of n minus k. As we have already seen, I can also write this as h of n, x of n minus k and h of k. So let us stick to this type of equation, and then let us find out how do we do convolution for such cases. Okay, let us look at different cases available. So let us start with a case 1, okay, where n is equal to 0. When n is equal to 0, what is it I will get? I will get y of 0. So let us write down here. So I will get y of 0 here because n is 0. Now what will happen to this sequence? I can write this sequence as k is equal to minus infinity to plus infinity, okay, x of k and h of 0 minus k, that is, this will be equal to minus k. Now let us take case 1, that is, I will take n is equal to 0. N is equal to 0, this becomes y of 0. So this is summation k is equal to minus infinity plus infinity, x of k, h of n minus k. For us, what is n for us? N is 0. So this will become minus k. Now I have to do the summation. What is the summation starting from? The summation starting from minus infinity plus infinity. So it goes on from some place. Okay, let us start from something which is finite. So let us start with this minus 1. So k is equal to minus 1. This will be equal to x of minus 1. Okay, what is h of minus 1? That will be plus 1, h of 1 here. Okay, plus, then we will move to 0, x of 0, h of 0, plus x of 1, h of minus 1, plus so on. Okay, so let us look at this. So that will be how much? X of minus 1 is for us 1, h of 1 is how much? 1, okay, plus, okay, we will put a 0 because, we will put a 0 here because the sequence does not exist beyond, before this and beyond this. So we, even if you take the summation from minus 1 plus infinity, unless you reach minus 1, there is no value. That means you will get zeros only. Now we have shifted up to minus, that is the reason which we have taken from here. So that is 1, plus x of 0 is how much? That is 1, h of 0 is 1, plus this is 1 and this is 1, okay, plus if I look at the second term, then what is x of 2 is absolutely x of 2 does not exist. So whatever you do after this will all be zeros. So I can put zeros here. So what is the answer? 1 plus 1 plus 1. So this is equal to 3. Okay, so let us write down here y of 0 is 3. Y of 0 is 3 here. Similarly, let us take a case n is equal to 1, that is case 2. Okay, let us take a case 2. N is equal to 1. So what will be y of 1? Then this will be equal to y of 1. So this is summation k is equal to minus infinity to plus infinity, x of k, h of n minus k. What is n for us? 1. So this will be 1 minus k here. Well, let us do the summation again. Start from 0 somewhere. Then let us take x of 0 first, or x of minus 1 first. So what will happen? Start from here. So if k is, this is equal to x of minus 1, h of 2, okay, 1 minus of minus 1 h of 2, plus x of 0, then this will 1 minus 0, it will be h of 0, plus, okay, plus next one will be x of 1, h of 0, plus x of 2, h of minus 1, plus so on. So, if we look at this, then let us add these together, all of them. So, what is this for us? This is 1 and this is 0. So, start with a 0 here, plus how much is this? This is 1, this is 1, so this will be 1, whereas this is 1, this is 1, so this will be 1, plus this is 0. So, we will get this as equal to 2. That is, y of 1 is equal to 2. Y of 0 is equal to 3, y of 1 is equal to 2. Let us take this third case. So, let us take case 3. What is case 3 for us? We have taken case 1, we have taken n is equal to 0, case 2 we have taken n is equal to 1. Now, case 3 will take n is equal to 2. So, let us put this here. So, what I will get is, now it will be y of 2, that will be equal to k is equal to minus infinity to plus infinity x of k h of 2 minus k. 2 minus k. This is our general formula. From this, let us calculate. Let us see. So, therefore, y of 2 for us is equal to summation. Let us start from somewhere. X of k, let us say this is minus 1. Okay. Then h of 3, because this was 2 minus of minus 1 plus. So, that will become plus. Then x of 0, h of 2 here, 2 minus 0. Then we will take x of 1, then h of 2 minus 1, that is 1, plus x of let us take x of 2, and then there is no, actually there is no point, but because h of 0 is involved, we are taking this. So, this goes on. So, how much is this? So, because h of 3 does not exist beyond 1 either side, this is 0. As h of n does not exist beyond 1 on positive side, minus 1 on the negative side, h of 3 does not exist. So, what is this? This is equal to 0 for us now. Then this is also 0 because h of 2 is not there, whereas these are 1. So, that is 1 and 1, plus x of 2 does not exist. So, this is equal to 1 for us. So, what is this? Now, I can write this here, y of 2 for me is 1. Okay. Similarly, let us take one more case. Let us take n is equal to 3. Okay. Let us take that case 4, n is equal to 3. Then the formula here will be y of 3, because n is 3, this becomes k is equal to minus infinity to plus infinity x of k h of 3 minus k. Let us start again. Then y of 3 will be equal to plus x of minus 1 h of 3 minus of minus 1, that is h of 4, plus x of 0 h of 3 plus x of 1 h of 2 and so on. I see here this is 0, this is 0, this is 0. So, I will get here 0. So, what is n? Now, y of 3 is equal to 0. Okay, now, so far what we have done? We have taken n as positive. So, n is 0, 1, 2, 3. Now, let us calculate for n is equal to minus 1, n is equal to minus 2, n is equal to minus 3. How will your sequence look like? Now, we have considered a case for n is equal to 0, plus 1, plus 2, plus 3. Let us look at what happens when we take n is equal to minus 1, minus 2, minus 3. So, that we will get a basic understanding how is your system getting convolved in a certain range of values. Let us start with n is equal to minus 1 now. That is case 5, I will take n is equal to, case 5 I will take n is equal to minus 1. So, what will be my y of minus 1? This will be equal to k minus infinity plus infinity x of k h of minus 1 minus k. So, let us see this value, how much we will get. Let us see now, see the summation now. So, y of minus 1 is equal to adding. So, this will be minus 1 here. So, h of minus 1 plus 1, that is 0, plus x of 0 h of minus 1, because this is 0, then x of 1 h of minus 1 minus 1, that is h of minus 2 plus so on. Okay. So, this I will get this as, this is equal to 1 for us, this is again equal to 1, that is 0. So, I will get 2 here. That is, let us write down this here. Let us write down this here. So, y of minus 1 for me is equal to 2. Minus 1 is equal to 2 here. Now, similarly, let us take another case. N is equal to minus 2 here. So, y of minus 2 will be equal to k is equal to minus infinity plus infinity, x of k, h of minus 2 minus k. So, let us see how much is this value. Okay. So, y of minus 2 for us is like this. So, let us start again the summation. X of minus 1 we take, then h of minus 2 plus 1, that is minus 1, plus x of 0, h of minus 2, okay, plus x of 1, h of minus 3, and so on. Okay. So, this is equal to, this is 1 for us because both of them exist, h of minus 2 the system does not exist. So, this becomes 0, this of course also does not exist. So, this becomes 0. So, what is y of minus 2 for me? Is equal to 1. Let us similarly look at the other case, that is where n is equal to minus 3. Let us take now the case 7. Okay. Here n is equal to minus 3 for us. So, what is y of minus 3 here? Y of minus 3 will be summation k is equal to minus infinity plus infinity, x of k, h of minus 3 minus k. So, let us see what is the value of this. So, y of minus 3 is equal to, okay, x of minus 1, h of minus 3 plus 1, that is minus 2, okay, minus 3 plus 1, that is minus 2, plus x. So, let us take x of 0, this will be h of minus 3 plus next x of 1, h of minus 3, that is minus 2, plus so on. So, look at this, this is 0 for us, this is 0, and that is also 0, and goes on. So, we will get an answer of y of minus 3 is 0. So, let us put it here, y of minus 3 is 0. Okay. So, these are the different values which we got. Now, let us, you can generalize actually. When you look at this, the system when convolved, y of n is 0 whenever the value of n is plus or minus 3. That is one point. The second is, this is 1, y of n is 1 when n is equal to either 2 or minus 2. Similarly, y of n is equal to 2 when n is equal to either 1 or minus 1. So, let us summarize this here, we can put it here, all these cases. Let us just write down there. So, y of n is 0 whenever it is minus 3 or plus 3 or beyond, that is n existing between plus 3 and minus 3. This is y of n. Y of n is 0 in two cases. One of them is when n is equal to plus 3 and n is equal to minus 3. So, we have put this here. Similarly, let us take the second case, y of n is equal to, let us take this case now. Y of n is 1 when n is equal to plus or minus 2 here, 2 here. Okay. Similarly, we will take another case here. This we have taken, this we have taken, and this also we have taken, isn't it? And y of n is equal to 3 when n is equal to 0. So, these are different values. Let's draw the sequence here. Now, the sequence looks like this. This is my convolved sequence y of n. See here, n is equal to, this is my n. So, 0, this is having a value 3 here, this is 3. Okay. And let us take this plus or minus 2. Let us say this is plus 2 and this is minus 2. Then it is having a value of how much? 1 here. So, this is 1 here and this is 1 here. Also, if you look at this, there is again y of n is equal to 2. Here, if you look at these two cases, when n is equal to plus or minus 1. So, this will be equal to 2. This is 1 for me, this is 1 for me, and this is 1 here, and this is 1 minus 1 here. So, this is having a value of 2 here. So, this is how y of n looks like. So for y of 1, this is having a value of, which is having a weighing factor of 2 here, and for value of 2, it is having a weighing factor of 1, so this is 1. Similarly, it exists on both sides. So this is the convolution of x of n and h of n given functions. This is how it looks like.